In this video, we will explore the agroclimatic indicators a little further. With climate change, we often consider the difference between 30-year periods to see how our indicators are expected to change in the future. In this video, we are making an application where we can explore the 30-year average data for different world regions. I will go through a simple starter script. The script starts with two dictionaries, one for the different regions and one for the RCPs. These are loaded in the drop-down menus. We again see an output figure and our main application where we call our RCP and our region. We are retrieving two sets of data for two different climate models because I want to see the difference between the two models. Then I use cube average over the dimension time to calculate the average over 30 years. It is automatically averaged over a 30-year period because I retrieve the data for 30 years. Then, because I want to see the difference between these two data sets, I calculate the difference with a simple minus operator. Then, to plot these data, I add a projection, which is called in the figure. I am using one figure to plot three subfigures. Apart from the projection, I'm also loading the region that was selected in the drop-down menu, and I'm selecting a figure size. This figure size will not matter if we run inline. But if you open the application in a new window, you will see that it makes a big difference what figure size you select. By selecting the subplot, I'm ensuring that all my three figures use the same projection and the same extent. They have exactly the same layout. So we can see that there are some issues with the plot I've created. For one, the scale on the color bar of these plots makes it hard to see the difference between the two models. The script takes the minimum and the maximum value of the data to create this color bar. So if we focus on Europe, it does not show the detail that we want. It can also be that the color scale of the first and the second plot are not exactly the same. Another issue is that the plot takes the variable long name as the caption of the color bar. As you can see, that is not very suitable in this case. We can change all this with the p-color mesh quarks. Here we can add the color map, a minimum and a maximum, and a label. You can now see that the plots are much clearer. So in this example, I've chosen 50 as a maximum value. But you can imagine that this maximum is too low if we are counting consecutive dry days in Africa. This static maximum might not be very useful. So I want to add an option to change the extent of the map. I do this by adding an input I need to add the maximum days here, and then I can use it for Vmax. So we can now change the extent over here. We can also play around with the projection. We can choose a different one. And you can see the plots look slightly different. We can even tweak which coordinates the projection is centered around. By adding the coordinates per region and adding them into the projection. The cdsplot.geomap function is only one way of plotting maps. Another option is the map.plot function. I will add this one in a different figure. As you can see, this type of plot has a different way of defining the style. So in this specific style, I'm using the contour level list with the numpy arrange function. To use this in the C3S Toolbox, I have to import the numpy library. It is very useful that we can use some general Python libraries in the C3S Toolbox. As you can see, the map.plot has a different output. Now to round off this application, I want to add a nice caption. For this, I add a markdown, a caption, and I return the caption. I now have a fully functioning application where I can compare different climate model outputs for the consecutive dry days. The next step is to work with multi-model ensembles and comparing different time periods.